Okay, so we'll start with a geometry network. I'll call it sim. Let's change the color here. Let's dive inside and create a grid. So this grid is too big for our simulation, so I'll change the size here. And I'm changing the size with respect to the image that we'll be using for attribute from map. So the size is 2.106 by 2.407. Okay. And I'll change the rows here to 2000 and columns here to 2000. So we have a lot of points here, a lot of geometry. If I close in, zoom in, you can see you have a lot of points here. Okay, so we are doing that for our attribute from map so that we can get the proper image projected on our grid. And here I'll choose the image, and this is original Adidas logo. This is what we are getting. I'll just invert it, invert U, no, invert V. Yes. So let's change the CD attribute from vector to float, and this is our Adidas image projection from map. Okay, so this size, as I said earlier, this is the size that is with respect to the original image that I've used here. Okay, for attribute from map. So after the attribute from map, what we are going to do is we'll create a blast node, and I'll blast all the geometry which has a color black. Okay, so @cd is equal to 0, and we are deleting all the points which had a black color, so that we are good to go with only the Adidas logo here. Okay, so this is what we are getting, and that's what we wanted. After this, what I can do is I'll use a node called attribute delete, so that we will be deleting the color CD attribute. Okay, we need to delete that, otherwise when we exclude that it will cause some problem. Let me just close it. Okay, so after the attribute delete, we are going to use a poly extrude node, and this poly extrude node, we will be extruding our geometry downside. So let's see something around here. So let's change the distance here to something like 0.126 or 128, and let's just let it process it. Okay, so this is what we are getting. Let me increase the number of divisions here to 5 so that we have some divisions here in the middle here. Let it process. Yeah, okay, so this is what we are getting, and let's just output back. We'll turn it on so that we have a back here, otherwise it would just be flat, there would be nothing here. Okay, so we have our geometry now, and what we can do is I would like to make a better attempt at creating or remesh it. So I'm using a VDB from Polygon here. So that is that, and this is what you're getting, which is actually even worse. So let me just decrease the voxel size to 0.05. 0.05 seems to be working good for this one. And what we can do is I'll use a VDB smooth. VDB smooth SDF. Okay, and this will just smoothen our geometry here. So let me just bring the iteration down to 2, and I'll change the operation to mean curvature flow so that it maintains its original shape. Okay, and after the VDB smooth, we can convert it back to polygon. So convert VDB and change it to polygon here, convert to polygons, and this is what we are getting, and this actually looks quite good now. It has our shape, the shape that we wanted. It has been smoothed out, but the point count is too much for this simulation, for this specific simulation. So I'll just use a poly reduce node, and I'll reduce the geometry by 50%. Okay, so now we have our mesh with the exact same shape, but the geometry has been reduced. Okay, and now what can do is I'll use a UV project node so that we will have some UVs on this geometry, because later on, as you can see in the preview, as you saw in the preview, we have used some textures here. Okay, so this is inverted, so let me just rotate it by -90, and I think that will be able to fix our UV problems here. Otherwise it was inverted before. Okay, so after the UV project node, as you can see, I think we can work, or we can increase the size here. As for this specific simulation, I think the size was bigger than this, so I've used a box here just to compare it. So I'll be using a transform node, and let me just increase the size here by 3. So I'll change the uniform scale to 3. Okay, so this is looking better. Yeah, this is looking better. So what I can do is I'll just move it up a bit so that this is sitting just above the ground. Okay, so what I can do here is I should increase the size a bit more, maybe by 1.5 times. So let me just use another transform node, and I'll increase the uniform scale by 1.5. Okay, so what I'm going to do here is I'll just move it up a bit in the -z direction so that it is sitting in the middle of our world origin. Okay, something like this. So the middle of the geometry is at 0, 0, 0. Okay, so this is looking good. What I can do now is I'll just create a group node here, and all the bottom points of this mesh, I want them to be pinned. I do not want them to take participation in the simulation. I want them to be pinned at their position. So I'm using a group, and group type is going to be points, and I'm changing the name to pin. Let me just turn off the keep in bounding box, and this is the bounding box. Let me increase the size in the X direction so that it covers everything in the X, and in the Z as well. I'll increase the size, and I'll just bring it down a bit so that it is including all the points at the bottom of this mesh. Okay, something like this. Maybe I'll bring it up. So all the points at the bottom of this geometry are selected, and some of them are here missing. So let's just increase the size in the Z so that everything is covered. Okay, and these points will not take participation in the simulation. They will be pinned. Okay, so that is that. After this, maybe I should just increase it a bit. Yeah, something like this. Okay, so after this, what I'm going to do is I'll be using another group, and this group will consist of all the points in this geometry, in this mesh. Okay, so I'll just call it cloth, or cloth all, or all, whatever you want, you can call it. All these points will be taking participation in the simulation, and I'll be running all my constraints on all these points. That's why I've used this group. I created this group. After this, let's create a Vellum balloon configuration. So this Vellum balloon configuration, what this will be doing is it creates two important cloth properties, two important cloth constants. One is cloth constant, and this cloth constant controls how stretchable the cloth is going to be and how bendable the cloth is going to be. Okay, and here in the stiffness, we control the stretchability, and in the bend section, we control how bendable the cloth is going to be. We have our pin to animation here, and we will select our pin points, which are the pin group. Okay, so if I select this, you'll be able to see that all the bottom points are being pinned. They will not be taking participation in the simulation. They will be pinned in their original position, and that's what we want. Okay, and After this, you can see, as I said, the stiffness, the stretch section controls how stretchable the cloth is going to be. The stiffness, if it is going to be very high, then the cloth is not going to be very stretchy, and that's what we want. So I have increased the stiffness to 6 into 1e plus 10. Come to the bend section, and we want the cloth to be quite bendable, so I'm decreasing the stiffness to 0.001, something like this. Vellum pressure. I'll just change the group type to points here, and I think I've not used our group called cloth here. So let's come to the vellum cloth constant, change it to group type points, and select our group which is cloth, and do the same to our vellum pressure constant. Select our cloth group so that these constants will be applied to all our points. Okay, so the stretch section, in the pressure constant control maintains the amount of pressure inside our vellum solver, and it also increases the amount of pressure inside the mesh. Okay, so the stiffness control maintains the amount of pressure inside our geometry, so I want to maintain the pressure quite healthily. I want the pressure to be quite good, so let's just keep the stiffness at around 10 into 1000. So the stiffness is going to be 10,000. Okay, and the rest length scale controls the amount of pressure that we are increasing, that we are generating inside of our geometry. So if I increase the rest length scale here to 1.25, that means the volume or the pressure is going to be 1.25 times of its original volume. Okay, here I am turning on the group, and I'm calling this group pressure, so that if we want to manipulate any of these properties, pressure properties inside our vellum solver, we'll be able to do that with the help of this group. We will be able to define specifically those properties. So this vellum solver, I'm connecting it to our vellum constants, and as you can see, everything looks fine. I'll just turn on the ground position here, and you can see that our geometry is a little bit up, as we have moved it up in the y direction by 0.02, so it is not at all colliding with our ground plane, and that's what we wanted. Come to the forces, there's gravity, and everything looks fine. I think what I can do is I'll just increase the substeps to 4. Okay, so we'll be using grains later, we'll be using rigid bodies for our vellum later, so substep 4 will be working fine with them as well. So that is that. Now what we can do is we can run this sim. Okay, so this is what we are getting. Our mesh is behaving like our balloon as expected, as we had increased the rest length scale here. So the pressure is 1.5 times of its volume, and it's looking quite good actually. But this is the rest length scale, and because we have increased that, our pressure inside our geometry has been increased. This is looking good, but what if you want to control the areas in which the pressure is more, and rest of the area the pressure is going to be less? For that, what I'm going to do is we'll be using an attribute called Pressurescale. Okay, Pressurescale. This is the attribute we will be using, so I'll just demonstrate how it works. So let's take a attribute from paint. Attribute paint. Okay. So this is the attribute from paint node. Attribute paint node. And what I can do is I'll paint some attribute here. I'll come to the attributes here. I'll just rename this to Pressurescale. So we are going to be painting Pressurescale attribute on our geometry. Okay. So initially the Pressurescale is going to be 0. So our geometry has 0 value of Pressurescale attribute. I'll just turn off the textures here so that we can see it properly. And now I can paint a value of 1 on this geometry, Pressurescale value of 1. Okay, so let me just increase the size here of the brush. Maybe I can control it from here, or yeah, here's the radius here. So let me just increase it to 0.45, And now if I paint it, you can see the geometry initially had a pressure scale value of 0, and now wherever I am painting it, the value there is increasing by 1. Okay, so all these points on this geometry, their pressure scale value, the pressure scale attribute has been increased to 1. Okay, and now let's see if I run this, what is going to happen. So the pressure scale attribute is a built-in attribute for Vellum Solver. You don't really have to, let me just visualize it as black and white, so I'll just change it to grayscale. Okay, so this is it. Wherever it is white, the pressure scale value is 1, and wherever it is black, the pressure scale value is 0. Okay, so the pressure scale value is actually a built-in attribute for Vellum, and you don't really have to turn it on or anything. It will be working fine. So let's just run this and see what we are getting. Ideally, wherever the pressure scale attribute is 1, there it should inflate a lot more as compared to the areas or geometry or points where the pressure scale attribute value is 0. Okay, what the wrestling scale does is it applies or it generates or it increases the pressure. It increases the pressure equally on all the points. Okay, but if you want to manipulate some of the areas of the geometry where you want the pressure to be more and some areas you want the pressure to be less, pressure scale attribute is the key to go. And as you can see, wherever we have a pressure scale of 1, the geometry is inflated properly, but wherever the pressure scale value is 0, those areas or those points are not properly inflating. Okay, I think I'll just reset it and I'll decrease the radius and I'll just paint it again so that maybe we can have a better look. Let's just decrease the foreground. I actually wanted the foreground to be at 0.01, but let's just play with this. So the radius is going to be 0.18, which is quite low. Okay, something like this. This is thinner compared to the last one. And if I paint it like this, something like this, so I'm painting some of the areas, some of the points with a pressure scale attribute value of 1, and the rest of the geometry has a pressure scale attribute value of 0. So now when we run this, I think we should be getting a proper contrasty result here. So let's run this and see. Okay, so this is what we are getting. This is what we are getting, and I think it is explaining what I was trying to tell you, that all the geometry which had a pressure scale attribute value of 1, the inflation there is working fine, and rest of the points where the pressure scale attribute value was 0, the inflation is not there. And that's what we wanted. So we can control inflation not just with our wrestling scale or our stiffness in our pressure constant, but also with the value of the pressure scale attribute. Okay, so this is good for static geometry. If you do not want the pressure scale to change, this was a good solution. You can just paint it, or you can group some of the points and give them specific values. But what if you want a dynamic pressure scale? What are you going to do about that? For that, what we can do is we can bring that pressure scale value inside our Vellum solver. So let's just create the pressure scale here. I'm using attribute triangle and f at the rate pressure scale. Let me just keep the pressure scale at around 0.005. Okay. For this geometry, the basic pressure scale value is 0.005. Okay. And after this, I'm going to create a box with the help of which we will be transferring some of the pressure scale attribute. So this is our box. Let me just template this and let me make this box bigger. So let's increase the size here in the Z direction, something like this. And another thing that I want is I want to decrease the size in the X direction. So I want it to be a lot thinner, something like 0.56. And maybe I can make it more specific here as well, 15.3. Okay, so this is our box. Let me just come here, look it from this perspective and move it up a bit. Okay, so I'll just move it up, move it up a bit so that only some of the points are touching, are colliding. And yeah, this looking nice. Maybe I'll make it specific 0.96 and this is working fine. That's what we want. And I'll just increase the axis divisions here as well. Okay, because we'll be using attribute transfer node and we will need points in the middle to properly transfer the attributes here. So let me just first rotate it a bit as well. So I'm using a function at the rate frame multiplied by 3 so that as the simulation progresses, the box will be multiplying, and I have decreased the timeline to be at about 150 because we do not want more than 150 frames here in our simulation. And as I said, let's just increase the axis division to around 32 by 32 by 32 so that we have enough points in the middle here. Okay, so we have a box that is rotating as the simulation progresses, and here we will give the value of 1. So I just copy the attribute triangle, and to this box I am giving a pressure scale value of 1. Okay, so our geometry, our main geometry, which will be in the simulation, has a value of 0.005. Okay, and the box that we will be using to transfer the attribute has a pressure scale value of 1. So after this, let's just use a attribute transfer node. Okay, so let's use a attribute transfer node here. Let's connect this to our geometry and this point, this input to our box. Turn off primitive, select pressure scale in the points because pressure scale is the point attribute that we want to transfer. And okay, so everything is 1. That means the pressure scale is equal on the geometry everywhere. Why is that? Let me reset this viewport and let's see. Okay, turn this off, turn this on. Pressure scale, can't visualize it properly. So the pressure scale value here is 1 and here is 0.05. So maybe let me come to the pressure scale and the minimum value, let me just make it to 0.005 instead of 0. Maybe this will help us and we can visualize it. Okay, if the marker is used, let's see, so the values everywhere is 1, and I think what we can do is come to the attribute transfer, make it color, ramp from attribute. Okay, what I can do here is come to the attribute transfer node, come to conditions and change the distance threshold here to around 0.015, something like this. 0.015, and if I increase the blend width here, you can see we are getting our attribute transfer here properly. Okay, so wherever the box is colliding or it is in contact with our Vellum geometry, our simulation geometry, the attribute is being transferred. Let's make it up. I'm just moving the box a bit up and down just to see if there's any proper effect here, if it is affecting the attribute transfer in any positive way. So I think I'll just keep it at here. Okay, and maybe I should just play with our blend value here. Come here, I'll increase the blend width to something like this, and I'll also increase the distance threshold to 0.15 instead of 0.015. So now blend width is 0.38, and maybe I can increase it a bit more. So this is our geometry, and as you can see, the attribute is being transferred from the box, which has a pressure scale attribute of 1, and this is how it is looking. Okay, wherever it is white, there the box is transferring the attribute, the pressure scale attribute of 1. Okay, so we can bring this attribute inside of a Vellum solver. So what we can do is, let's create a null, and I'll call it out. Okay, so this is, maybe I can rename it to out pressure scale. Okay, and now we'll be able to bring it inside of a Vellum solver. So let's dive inside our Vellum solver, and it is running. So let me just stop it by pressing escape, and let's turn off our brain here so that we can work in peace. Let's create a geometry wrangle to bring in our pressure scale attribute inside of a Vellum solver. So geometry wrangle, let's connect it to force and go to group, and what we want is, we want this to only affect our cloth group. Okay, the small letter cloth, because we have created a group here called cloth, which consists of all the points here, and we have used that group cloth inside of our constants as well, in the cloth constant and in the pressure constant. So it is a good practice to just use group here as well. Okay, so let's come to the input, change it to SOP, and we will be bringing in our null, which is out pressure scale. Okay, so it is connected now. Let's create a pressure scale attribute here. So I've @ pressure scale. We want it to be equal to the pressure scale which is outside. So let's use a point function. Point 0 represents this input, the SOP that we have created here. Okay, and we want the pressure scale attribute. So we are writing pressure scale, and we have this pressure scale attribute here, and this is our null which we are using to bring in our pressure scale. Okay, and it is connected to our input 0 here. So pressure scale attribute, and we want this pressure scale attribute to be on the point numbers. Okay, so if you go outside, and if you go here and turn on the point number, and if you turn on the visualization for our pressure scale, what you will be, let me just reset. Okay, so now you can see some of the points here have a pressure scale value of 1, like this point, and some of the points here have a pressure scale value of 0, like this point, or 0.05, like this point. So what we want is, we want all these points to get updated with their pressure scale inside our Vellum solver, and that's why we are using this point function. Okay, so point function 0, which is the input, pressure scale attribute, which is running on all the point numbers. We want it to update it inside our Vellum solver. Okay, so what we can do now is, we can run this simulation and let's see what we are getting. go outside and let's run the simulation. Hopefully it will work fine, and let me just reset viewport as we cannot see anything here inside our Vellum solver. Okay, so now let's run this simulation and let's see the result. Okay, so this is what we are getting. The pressure scale is moving as we wanted it. Okay, so this is looking quite nice. What we can do is I'll use a Vellum post process just to make it a bit more good looking. I'll not be changing anything at this point. I'll just turn the smooth shaded, and I'm using a color here, color attribute, color node, and we'll change the color on the basis of a attribute. So change the color type to ram from attribute, and we'll be using the attribute none other than pressure scale. Okay, so wherever the value is 0, it is black, and wherever the value is 1, it is white. So let's change the colors here. So something like this. So wherever the pressure scale value is 0, it is orange. Wherever the pressure scale value is 1, it is blue. And now if we run this, we'll be able to visualize it properly and smoothly. So this is looking quite nice actually. So let's run the whole flipbook, the complete flipbook, and let's see if it is something that needs changes or if it is working fine. Okay, so this is looking fine to me. If I run the simulation, if I run this, look at this. The geometry is inflating only on those places where the pressure scale attribute is 1 and everything else is quite deflated. And that's what we wanted, right? So this is how you use pressure scale along with the wrestling scale value of pressure constant and all the other things that you can use to control our pressure. The next thing that we'll be creating is Vellum rigid bodies in this tutorial. Okay, so the Vellum rigid bodies are different with respect to the rigid bodies, the RBDs in Houdini. Okay, the RBD simulations. The Vellum rigids, as I'm calling them now, we can create them with the help of Vellum grains or Vellum shape match. Okay, and why they are useful? Because if we are simulating something as rigid inside of a Vellum solver, what happens is that rigid body or that specific Vellum rigid will be able to react with other Vellum properties. Like if we are creating Vellum cloth, then it will react with Vellum cloth, and if we are creating Vellum fluid, then that Vellum shape match rigid body that we are creating will be able to react with our Vellum fluid. So with the help of the Vellum rigid bodies, we'll be able to do that. Okay, so let's do that now. Okay, so let's bring in our shoe geometry first. So we'll be creating our shape match rigid bodies, Vellum rigid bodies for our shoe. So let's bring the shoe here. So this is our shoe, and what I'm going to do is I'll use a convert node now. Convert, and let me just use a transform node to decrease the size to maybe 0.01, something like this. And if I turn on the grid here and just template our cloth geometry or the Adidas logo, this is what we are getting. Okay, so let's work on this. What we are going to do now is we'll be creating Vellum grains or Vellum